Are we living in a simulation? In 1999, a film asked a question that millions of people couldn't let go of. Not because it was science fiction, because it felt like a warning. A man wakes up, goes to work, eats the same meals, follows the same routine, and somewhere, deep in a part of his mind he can barely access, something is wrong. Not broken, not traumatic, just off. Like a splinter he can't find. Like a word he can't remember. Like a rule he never agreed to, but has been following his whole life. The film was The Matrix. The question it asked was simple. What if reality isn't real? Most people left the theater and moved on, but some people didn't. Some people, scientists, philosophers, mathematicians, computer engineers, took that question seriously. Very seriously. And what they found, or what they think they found, is difficult to dismiss. Not because the theory is proven, because it might not be disprovable. Let's begin with what we actually know. The universe operates on rules, not suggestions, rules. The speed of light is constant. Gravity follows a precise mathematical formula. Electrons behave in predictable, quantifiable ways. This is not controversial. This is the foundation of modern physics. But here is something that is less often discussed outside academic circles. At the quantum level, the level of the very smallest particles, reality does not behave the way it should. Electrons, when not being observed, do not exist in a single location. They exist in what physicists call a superposition, a spread of possible positions described mathematically as a wave of probability. The moment someone measures the electron, the moment it is observed, that wave collapses. The electron snaps into a single, definite position. This is not a theory. This is a documented experimental result, confirmed thousands of times since the early 20th century. It is called the quantum measurement problem, and it has never been fully explained.
What it means, in simple terms, is this. The universe appears to only calculate a definite outcome when something is looking. This observation was made by physicist John Wheeler, who described it using the phrase, "it from bit." The idea that physical reality might emerge from information, from binary yes or no choices at the fundamental level. Wheeler was not a fringe figure. He coined the term black hole. He worked alongside Albert Einstein. His ideas are taught in university physics programs around the world. There is more. In 2003, philosopher Nick Bostrom at Oxford University published what is now called the simulation argument. It is not a conspiracy theory. It is a formal philosophical paper, peer-reviewed, published in the journal Philosophical Quarterly. Bostrom's argument is logical in structure. He presents three possibilities, which he calls the trilemma. 1. Almost all civilizations at our level of development go extinct before they develop the computational power needed to simulate entire conscious worlds. 2. Advanced civilizations reach that level of capability, but choose not to run such simulations for ethical or practical reasons. 3. We are almost certainly living in a computer simulation right now. Bostrom does not say which of these is true. He says that if the first two are false, if civilizations survive and choose to simulate, then the number of simulated realities would vastly outnumber the one original reality. And statistically, we would almost certainly be in one of the copies. This argument has not been refuted. It has been debated extensively, but not refuted. In 2016, a survey of physicists and philosophers at a major academic conference found that a surprising number of respondents considered the simulation hypothesis worth serious investigation. Not a majority, but far from a fringe.
In 2023, scientists at various institutions continued exploring what some call digital physics. The idea that space-time itself might be fundamentally discrete, quantized, and information-based rather than continuous. This is an active area of research, not a settled conclusion. These are the facts on the table. Now, let's look at the strange parts, the parts that don't quite fit. The first anomaly is something called the fine-tuning problem. The universe operates according to approximately 26 fundamental physical constants. These include the strength of gravity, the mass of an electron, the speed of light, the rate at which the universe expanded after the Big Bang. Each of these constants is a number, a precise number. If any of these numbers were slightly different, even by a fraction of a percent, the universe as we know it could not exist. Stars would not form. Atoms would not hold together. Life would be impossible. The odds of these constants taking the values they do by pure chance are so astronomically small that some physicists find them troubling. The universe appears, in some sense, calibrated for the existence of life. This is not a religious argument. It is a mathematical one. Some scientists explain it using the anthropic principle. We can only observe a universe capable of supporting observers. So, naturally, the universe we observe has the right constants. Others suggest multiple universes, each with different constants, and we simply happen to be in the one that works. But some researchers point out something else. Calibrated constants look a great deal like parameters, like settings, like values entered into a system before it runs. The second anomaly is more technical, but no less striking. In 2012, a team of physicists at the University of Washington, led by Silas Bean, published a paper exploring whether it might be possible to detect the structure of a simulation from within it. They were not claiming we live in a simulation. They were asking, if we did, would there be evidence? Their conclusion? Possibly yes. They suggested that a simulated universe running on a discrete lattice, a kind of three-dimensional grid, would leave a specific, detectable fingerprint in the behavior of high-energy cosmic rays. The particles would tend to align with the underlying grid structure. They would show what physicists call anisotropy, variation depending on direction, in ways consistent with a computational lattice, rather than smooth, continuous spacetime. The paper was published in Physical Review Letters, one of the most respected physics journals in the world. The footprint they described has not yet been confirmed, but it has not been ruled out. The third anomaly
involves mathematics itself. Mathematics is not invented. That is the position of many mathematicians and physicists. It is discovered. The same equations that describe the orbit of planets also describe the flow of electricity, the behavior of fluids, the structure of galaxies. The laws of mathematics appear to exist independently of the people who find them. Physicist Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences. He was puzzled, genuinely puzzled, by the fact that abstract mathematical structures, invented with no practical purpose in mind, turn out to describe physical reality with extraordinary precision. Some researchers ask, why should abstract logic match physical reality so precisely, unless physical reality is a mathematical structure, or unless both emerge from the same underlying system? The fourth anomaly is perhaps the most unsettling. We are building simulations ourselves. Video games from the 1970s could simulate a handful of pixels. Today's computing can simulate billions of particles interacting in real time. Virtual reality environments are already indistinguishable from the real world in limited contexts.
Artificial intelligence systems are now generating sensory experiences, voices, images, conversations, that people describe as real. The trajectory is clear. If this trend continues, and if human civilization survives long enough, we will eventually be able to simulate complete conscious worlds. Worlds where the inhabitants cannot tell they are simulated. We are already practicing. Several distinct theories have emerged from these observations. They exist in different forms, held by different communities, for different reasons. It is important to be clear, none of these are established fact. They are frameworks, interpretations, and, in some cases, beliefs. The computational universe theory. Some physicists and information theorists believe the universe is, at its core, a computational process. This view holds that what we call matter and energy are emergent properties of something more fundamental, information processing. In this framework, every particle interaction is essentially a calculation. The laws of physics are the operating rules of the computation. This theory is associated with figures like Konrad Zuse, who proposed it in 1969, and more recently with physicist Max Tegmark, whose work on the mathematical universe hypothesis suggests that all mathematical structures exist physically, that reality is, in some sense, mathematics itself. This is not a fringe position. It is debated seriously in academic physics. It is also far from universally accepted. The ancestral simulation theory. This is the version most directly connected to the matrix concept. It suggests that an advanced civilization, potentially a future version of humanity, or an entirely different species, has developed the computational power to run detailed simulations of conscious minds and entire histories. We might be among those simulated minds.
This idea is most associated with Nick Bostrom's 2003 paper, but it has been discussed and extended by many others since, including Elon Musk, who stated in a 2016 interview that the odds we are not in a simulation are 1 in billions. He offered no evidence for this specific estimate. It is an opinion, not a calculation. Some versions of this theory suggest that the simulator is not a distant alien civilization, but a future version of Earth itself, running historical simulations to understand the past. There is no confirmed evidence for any version of this theory. The quantum observer theory. A smaller group of researchers and philosophers takes the quantum measurement problem, the observation that particles only behave definitively when measured, as a potential clue. They suggest that the universe may be structured to avoid computing outcomes that have no observer, like a video game that only renders the parts of the world a player can see. This is sometimes called lazy rendering, by analogy with computing optimization techniques. The idea is speculative. Mainstream quantum physicists generally do not accept consciousness as the key variable in wave function collapse. The preferred interpretations, the Copenhagen interpretation, the many worlds interpretation, and others, do not require a simulator. But the comparison has not been entirely dismissed either. The glitch theory, a more popular and far less scientific variation, suggests that certain unexplained events, coincidences, or experiences might be errors in the simulation, moments where the underlying code becomes briefly visible. These ideas circulate widely in online communities and are not endorsed by mainstream science. Proponents point to things like déjà vu, recurring coincidences, or reports of reality feeling thin or artificial as evidence. Psychologists generally explain these experiences through well-understood cognitive mechanisms.
There is no documented case of a confirmed simulation error. This is important to note clearly. The glitch theory is not a scientific hypothesis. It is a belief, often held informally, sometimes humorously. It should not be confused with the formal philosophical and physical arguments described above. So what do the skeptics say? Most physicists, when pressed, will point to several fundamental issues with the simulation hypothesis. The first is the problem of computational resources. To simulate a universe convincingly, including every quantum interaction, every particle, every photon of light that has ever existed, would require a computational substrate of unimaginable scale. Some researchers have calculated that simulating even a small volume of space at the quantum level would require more computing power than appears to exist in the observable universe. The counter-response, that an advanced civilization might run the simulation at lower resolution, only rendering detail where observers are present, is technically interesting, but currently untestable. The second issue is consciousness. The simulation hypothesis generally assumes that simulated minds would be conscious, that they would have subjective experiences, just like non-simulated beings. But we do not actually know what consciousness is, or how physical processes give rise to subjective experience. This is called the hard problem of consciousness, and it remains entirely unsolved. If we don't understand what generates consciousness in our own case, we cannot confidently claim that a simulation could reproduce it. The third objection is Occam's razor, the scientific principle that the simplest explanation consistent with the evidence should generally be preferred. For most scientists, the simplest explanation for the universe we observe is that it is real.
Introducing a simulator, a civilization capable of building it, and a mechanism for consciousness to emerge within a computation adds enormous complexity without providing any explanatory advantage for the phenomena we actually observe. The fourth issue is falsifiability. A good scientific hypothesis must be testable. It must make predictions that can be confirmed or denied. Some versions of the simulation hypothesis, particularly the glitch and observer versions, cannot be tested at all. If any unusual experience can be labeled a glitch, and no experience can definitively rule out a simulation, then the theory explains everything and predicts nothing. The more rigorous versions, like the Bean lattice model, do make testable predictions, but those predictions have not yet been confirmed. For now, the mainstream scientific position is this. The simulation hypothesis is an interesting philosophical puzzle with some connections to real physics, but it is not supported by confirmed evidence. And yet the idea does not go away. It returns, again and again. In academic papers, in tech boardrooms, in philosophy classrooms, in conversations between people who have never heard of Nick Bostrom, but feel somehow that something about reality is not quite right. Why? Part of the answer is psychological. Human beings are pattern recognition machines. This is not a criticism. It is one of the things that made us successful as a species. We look for structure, for rules, for hidden causes. When we encounter something unexplained, we don't rest easily with, "we don't know." We reach for a framework, a narrative, a reason. The simulation hypothesis offers an elegant framework for almost anything. The fine-tuning of the universe, parameters, the strangeness of quantum mechanics, optimization, the feeling that something is wrong with reality, a bug in the system. It converts confusion into order. That is psychologically satisfying, regardless of whether it is true.
Part of the answer is also technological. People alive today have watched reality change faster than any generation in history. Photographs that looked real turned out to be digitally manipulated. Voices that sounded real turned out to be generated by machines. Faces that seemed human turned out to be artificial. Every year, the border between what is real and what is produced shifts further. This has, for many people, made the question of the authentic real feel urgent in a way it never did before. If we can fake a human face with a few seconds of video and some computing power, what exactly does real mean? If an AI voice can comfort someone, counsel someone, make someone laugh, does the substrate matter? These are not idle questions. They are questions that technology has made suddenly uncomfortably practical. There is also a historical dimension. Major paradigm shifts in human understanding have often involved the discovery that reality is not what it appears. The Earth is not the center of the universe. Time is not absolute. Matter is mostly empty space. The subatomic world does not obey common sense. Each of these discoveries was initially met with resistance, then with grudging acceptance. People who ask whether reality might be a simulation are in part asking, what is the next thing we are wrong about? History suggests that question is always worth asking. And there is one more factor, perhaps the most personal. For many people, the simulation hypothesis is not primarily about physics or computing power. It is about meaning. If reality is constructed by something, by someone, with intentions, then the universe is not indifferent. There is an architect. There is a purpose. There is, potentially, a way out. This mirrors the oldest human impulse, to believe that behind the surface of things there is a deeper truth, a hidden order, a reason. The Matrix was not a physics documentary. It was a myth.
And myths are powerful, precisely because they speak to something in us that data cannot reach. Here is where we are. A small but serious group of physicists believes the universe might be fundamentally computational. Their arguments are mathematical, and in some versions, testable. A formal philosophical argument, Bostrom's trilemma, suggests that if advanced civilizations survive and simulate, we are statistically likely to be inside one. The argument has not been refuted. It has been criticized, extended, and debated, but not refuted. Quantum mechanics continues to behave in ways that are strange, deeply counterintuitive, and not fully explained. The role of measurement and observation in determining physical outcomes remains philosophically contested. The universe appears fine-tuned in ways that have not been fully explained by chance, by multiverse theory, or by the anthropic principle. Some physicists are troubled by this, others are not. We are building increasingly realistic simulations ourselves. We do not know where this ends, and we do not know what consciousness is. That last point deserves a moment. If we do not know what generates consciousness, if we cannot explain why reading these words produces an experience, an inner life, a sense of something happening, then we do not know what it would mean for that consciousness to be simulated. We do not know if a simulated mind would suffer. We do not know if it would dream. We do not know if it would be, in any meaningful sense, real. These are not questions that belong only to physics. They are questions that belong to every person who has ever looked up at the sky and wondered what exactly they are looking at. So ask yourself this, not as a question of science, not as a question of conspiracy, as a genuine question. You experience the world through information. Light hits your eye, converts to an electrical signal, and is processed by your brain into what you see.
Sound is pressure waves, interpreted. Touch is electromagnetic repulsion between electrons, translated into sensation. Everything you have ever experienced has come to you through an interface, processed, filtered, rendered. You have never experienced reality directly. None of us have. At what point does that distinction between experiencing information and experiencing reality begin to matter? The Matrix was fiction, but the question it was asking was not. And that question, that specific, strange, persistent question, has not gone away. Maybe it never will.